Hello and welcome to the first video of the M2 chapter Variable Acceleration. A quick M1 question on constant acceleration on the screen to get us going. The initial velocity of a particle moving with constant acceleration is this. So this is the acceleration, this is the initial velocity. Find the velocity of the particle after 4 seconds. So here we've been given 3 pieces of information. The acceleration is, I prefer column vectors rather than ij notation, so I'll write it like this. The initial velocity is this, and the time we're looking at is 4 seconds. We need to find the velocity. So we're using a constant acceleration formula because the acceleration is given here constant. The formula we need is v is equal to u plus at, and these 3 are vectors. So v is equal to -1, 2, plus the time is 4 times a, 3 minus 1, which gives us 11 and -2. Now although I prefer the column vector notation, because the question gave me it in ij form, I'm going to finish by writing it back in the same form as the question had. And there we go. An overview of the chapter. In this video we're going to understand that displacement, velocity and acceleration may be given as functions of time. We're going to look at using differentiation and integration to solve kinematic problems, and then we'll apply that calculus to solve problems involving vectors, and also to derive the constant acceleration formulae that we have been using before and which you know so well. The main purpose of this video is to show that your pure work and your mechanics work can overlap. So we already know that velocity is a change in displacement with respect to time, and acceleration is a change in velocity with respect to time. We can also have a change in acceleration with respect to time. We don't have a particular term for this, but it's increasing or decreasing acceleration. In all of these cases, we have the independent variable time and the dependent variables, displacement, velocity, and acceleration, changing with respect to time. And each of these ideas can be written as a function of time. So for example, if we've got a change in displacement, let me call that s, and that can be written as a function of time. Same with the other two, velocity could be a function of time, and acceleration can be a function of time. So rather than having formulae, fixed constant acceleration formulae like we've had before, we could have any function here. And these could be linear or quadratic, they could be trigonometric, exponential, they could be pretty much anything that you've done in your pure work so far. And you need to be able to use them as you would in your pure work. So we've got a few examples here, fairly straightforward. A body moves in a straight line such that its displacement s meters from a point O at time t seconds is given by this function here, for t greater than 0. Find s when t equals 2. That's a very simple bit of substitution. When t is equal to 2, s is equal to 2 times 2 cubed minus 3 times 2, which gives us the answer of 10. Part B is very similar, but now we're going to substitute a distance or a displacement and find the time. So we want the time taken for the particle to return to O. Now the difference between displacement and distance is very important here. When the particle returns to O, the distance is how far it's gone and then how far it's come back. But the displacement is the distance from its starting point. So when it returns to its starting point, the distance from its starting point is 0. So part B is asking us to find t when s equals 0. And when we put that in, we get an equation to solve. It looks horrible because it's a cubic, but we can factorize out one of those t's to get a quadratic. And we know that t equals 0 here is one of the answers, but not the one that we want. That's just telling us that at time equals 0, it starts at 0 displacement from its starting point, which is very obvious if you think about it. And this one here gives us 2t squared minus 3 has to equal 0, which gives t squared equals 3 over 2. And t to be plus or minus square root of 3 over 2, but of course in this case we can't have a negative t, not only because time shouldn't really be negative at all, but because it's specified in the question here t is always greater than 0. T is greater than 0, therefore t is equal to root 3 over 2. Our second example has a similar feel to it, but is a very different sort of question. A toy train travels along a straight track, leaving the start of the track at time t equals 0. It then returns to the start of the track. The distance, not displacement, s meters from the start of the track at time t seconds is modelled by the equation this, where t is between 0 and 4. Now the question is simply explain the restriction for the time to be between 0 and 4. The left-hand side of this restriction probably strikes you as quite easy. Of course the time has to be greater than or equal to 0, because we're told it starts at time equals 0 and time runs forward, not backwards. But why does it have to be less than or equal to 4? You can do this in a couple of different ways, but effectively what you're going to do is have to consider what happens when t equals 4, and when t is greater than 4, why is that a problem? One good way of doing this is to sketch a graph. We'll do that in another example. In this case, I'm just going to look at the numbers. If I put in t equals 4, we get s is equal to 4 times 4 squared minus 4 cubed, and that gives us a 0. When t is greater than 4, that cubic term is going to overpower this quadratic term, and we're going to get a negative answer, so s will be less than 0. In the previous example, that would not necessarily have been a problem. Displacement can be less than 0 because displacement is a vector. But in this case, we're told it is a distance, and distance is a scalar and cannot be negative. So what I would write here, after having done that, I would say distance is a scalar, and so cannot be negative. Therefore time has to be less than or equal to 4. Now on the other side of it, I just need to say the motion starts at t equals 0. Therefore the time has to be greater than or equal to 0. And that explains both sides of the inequality restriction here. If you wanted to do it graphically, that would be quite easy as well, except that you need to be able to sketch the graph, and that's not always straightforward, depending on what the function is. In this case, we can see we've got a repeated root at t equals 0, and it's a negative cube graph, so it comes down like this, and down there like that. So if I quickly sketch that on, it's something like this, where this is s, this is t, and from the work we did over here, we know that this value here is 4, and we can see from inspection that that's 0 there. And this is telling you more or less the same thing. Less than 0 on the time axis, time is not valid, and greater than 4 on the time axis, the distance is not valid because it's negative. And I hope you can see that it's not really adding or taking away anything from my answer, it's just using a diagram to help show that this is the case. Next example. A body moves in a straight line such that its velocity v at time t seconds is given by the equation this, for t is greater than or equal to 0. Find the initial velocity. Part A is fairly straightforward. For the initial velocity, that's just when the time is equal to 0. Substitute that into the equation, we get 0 minus 0 plus 24. So the initial velocity is 24. Part B, find the values of t when the body is instantaneously at rest. That means when v is equal to 0, we need to find t. Again, fairly straightforward. We just put that into our equation and solve it. In this case, we're going to need to solve a quadratic. If I divide everything by 2, I get t squared minus 8t plus 12. I think we can factorize that. We can have minus 6 and minus 2. So our 2 times t is equal to 6 seconds, and t is equal to 2 seconds. Part C, find the value of t when the velocity is 64. Very similar. We just substitute in the value of v. In this case it's 64. So we get 64 as part of the equation that we have to solve. Make a 0 on one side, and I'll divide everything by 2 as well at the same time, which gives the equation t squared minus 8t minus 20. This again will factorize, minus 10 and plus 2. So our two mathematical answers here are 10 and minus 2, but because t must be greater than or equal to 0, we have to reject this answer. Therefore, our final answer is t equals 10 seconds for part C. Part D is a little bit more interesting. We need to find the greatest speed of the body in the interval from 0 to 5. I need a bit more room for this. The reason I say it's a bit more interesting is because the phrase the greatest speed immediately makes me think of a maximum point, a turning point. And we know a couple of different ways to find a turning point. One of them is differentiation, but we'll leave that to another video. Another way is to complete the square. So if I complete the square here, we get 2 t squared minus 8t plus 24, and then that will become 2t minus 4 all squared minus 32 plus the 24 that's already there gives me a minus 8. And that tells me that the minimum or maximum point happens at t equals 4, and that gives v equals minus 8. Now what makes this more interesting is that I can't be sure that that is the maximum or greatest speed of the body. Either this is a minimum point, in which case it's probably not very helpful either way, or it's a maximum point, in which case because it's a negative value, it also will not be the greatest speed. To explain this, a diagram is going to be far more helpful to me. Here is a quadratic, so we should be able to sketch this fairly easily now that we've got this point here. 4 minus 8, let's say, is down here somewhere. So to explain why this as a turning point is not really very helpful in this case, let me sketch out a few different possibilities. It could be that this is the greatest speed, because if I have something that looks like this, where this is a minimum point, and these values do not get higher than 8, then minus 8 would be the greatest absolute value, and it would be the greatest speed. However, it could be a minimum point where the positive values go higher than 8, in which case something like 10 here, that would be the greatest absolute value. Now, strangely, if it's a maximum point, that's the least helpful of all, because if it's a maximum point, that means everything else is lower down, and in absolute value terms, everything else is going to be bigger than that. So the greatest speed would simply be the value either at 5 or at 0, depending on which of those two extremes was the biggest absolute value. So in this case, we really do need this diagram. And we also know that if we put t equals 0 in here, the v-intercept on the v-axis, if I label this, is 24. So that's way up here somewhere. And immediately we can see that 24 is a bigger absolute value than minus 8. So this must be a minimum coming down like this. And we actually also know these 2 points because we found this in part B. This is 2 and this is 6. So another way to find this minimum point would have been to use the symmetry of the graph. Regardless of that, we can see now very clearly that if we cut off at t equals 5, according to this restriction in the question, that's still down here. It hasn't become positive again. So the biggest value in absolute terms is this one here, 24. So while it's my instinctive reaction to do something like this, or probably more likely to differentiate when it talks about the greatest or smallest speed, I have to be a little bit careful here, because just finding a turning point doesn't necessarily give you the maximum absolute value. For this reason, I would recommend that if you can, you sketch the function to help you with a question like this. So here, the final answer, the greatest speed, actually happens when t is equal to 0, and it's 24. I hope that's enough for you to have a go at the questions in exercise 2a. Maybe I'll see you in the second video.